Dear students, now we take module 4 of our unit 3, right? That is related to FIR filtering of long data sequence. So in previous module we have seen the relation between circular and linear convolution, and particularly the application to the FIR filter. And FIR filter always have a finite length, capital M, and this input to this filter Xn also is having finite length, say capital L. But if capital L is very large, or if it is infinite, what we can do to apply this DSP, or you can say circular convolution, which is easier method to calculate the linear convolution. Say my input sequence action is very long, considered to be infinite length. For example, in speech or video streaming signal, the signal keeps on coming, so we can't handle it as a whole. So if action is of very large length, then you can assume the size of matrix becomes too large, right? When we calculate the circular convolution, when we want to calculate a linear convolution using circular convolution, the matrix size becomes too large to handle. So we cannot handle this kind of very large length sequence. So in some case, the input signal is not available as a whole, but available in chunks called the frames. So in some cases, it is also not available as a whole because it's a real-time streaming signal, so it keeps on coming. So we don't know the whole action signal, but it's come as a frame, say a frame of 100 samples, a frame of 200 samples, like that. So it comes in a chunks. Say for example, we are getting signal from some sensors. So sensors measures the physical quantity, converts it into the digital by some digital circuit, and using some microcontroller and some other associated circuit, it sends the data to our DSP. Then in that case, that data is always having, say, finite number of, you can say, samples. Similarly in a radar, so that's also sends the signal in a chunk, right? So also the limited memory in signal processing system limits the frame size, and whatever be the frame size, it should be limited because the frame is to be first stored in a memory. So whatever be the size of input buffer, that limits the size of this frame or length of the frame. So instead of using now sample based processing, we are using frame based processing. We consider now action to be made of different frames. Say, frame number 1 which consists 100 samples, frame number 2 consists of another 100 sample, frame number 3 consists of third 100 sample, and likewise. So the signal action keep on coming in a frame, and frame consists some block of the sample. So that is called the frame based processing, right? We are not taking individual sample, but a chunk of sample or group of sample, which is the frame based processing. So in case of the real application, when the signal is like this, we replace this linear convolution by sectioned linear convolution. Means first we take first a block of the signal, pass it through the filter, right, obtain the answer, then take a second block of the signal, pass it through the filter, take the output, right, like this. So we are doing linear convolution but in a section or framed manner. So that is called section or framed linear convolution. Remember, when we pass any signal Xn through the filter, it is always a linear convolution. But we want to perform it using circular convolution, and that is via DFT-IDFT approach and using FFT algorithms, right? Right now we are taking the circular convolution as a matrix multiplication. We can easily do it using the indirect method DFT-IDFT if we use the FFT algorithms, and that is practically done because FFTs are easier to implement inside the digital hardware, particularly in a DSP processor, right? So right now we concentrate, we want to do a linear convolution using the circular convolution, and we have seen we have to do the zero padding, proper zero padding, to obtain the same answer as linear convolution using the circular convolution, right? But here the question was this: action very long, then in case we are not handling it as a whole, so we are doing the section linear convolution. So equivalently we are doing section circular convolution. So there are two methods for performing section linear convolution. One is called overlap save method and second is called overlap add method. The overlap add method is very common, and we illustrate here overlap add method at present. So let me take my Xn is a streaming signal which is coming in a chunk of L number of samples, means its frame size is capital L. It has capital L sample in one frame, and it is passed through the FIR filter, and FIR filter is having length of capital M. So when I pass a sequence of length capital L through filter of length capital M, My outcome is the linear convolution, but the length of that linear convolution is capital L plus capital M minus 1. So let I consider this situation here, where I have first section or first frame of my xn, which is indicated here x1n is equal to x0, x1 up to xl minus 1. So that is L samples from xn first frame. Now I want to pass it through the FIR filter and I want to implement it using circular convolution. So I want the same answer as linear convolution. So first I have to do the zero padding. How many zeros I have to add after this? M minus 1 zero. So I will add some M minus 1 zeros. I collect the first L samples of this xn as a frame x1 and pad capital M minus 1 0. The hn is already I have, right, which is of m point sequence, and I will pad there L minus 1 0, right. So I have already hn, I will pad L minus 1 0 to it. So I will also make it of length capital L plus M minus 1. Similarly, I get the next frame x2n, which is now x of capital L, means it is starting from sample number L up to xl plus 1 and it ends at x twice L minus 1. But when I get this frame, I will also pad M minus 1 0 at the end and so on. So I get this xn like this, x1n, x2n in a chunk of L samples, but I am doing, when I get this L samples, I will do the zero padding with M minus 1 0 and my hn is ready with length of M, but it is also padded with L minus 1 0. And now I perform the circular convolution of how many points? Capital N is equal to L plus M minus 1 point with each x1, say xin, circularly convert with hn gives me the answer yin, but both of this are having this length. So this is same as this xin convolve hn. So this is a section convolution. x1n convolved with hn, x2n convolved with hn, like this, right? Now when I get this answer, it is L plus M minus 1 point, but my inputs are actually x1n was L sample, L length. So yn also should be of length, right? And I have padded 0 here, and then I have considered the next sequence to be filtered by hn. So what I need to do? I need to do some overlap and add. So last M minus 1 samples or last M minus 1 points for each block of this yin. In each yin, I get the last M minus 1 points, which are, you can say, extra, because I want only L points, right? When I pass x1n of L, I always want to get the answer of L point, but because of this linear and circular convolution, we are getting capital L plus M minus 1 points. But this last M minus 1 points are not useless. They actually indicate something. These are to be last M minus 1 point from each output block yi of n must be overlapped and added to the first capital M minus 1 points of the succeeding output block. So it is like this. To construct the signal yn, first I am getting the answer of this y1n. So I take y10, y1n up to y1l minus 1. Then last M minus 1 points, say y1l, I will add it with the first M minus 1 points of the y2n. That first point is y20. Then y1 capital plus 1 is added with y2 of 1 and so on. Similarly, I will do it for all the section convolution, y2n, y3n, y4n, like that. Now this is easier to interpret here in figure. So I have hn of length capital M padded with L minus 1 0. I have xn which I am getting in a chunk of capital L sample. So let I say this is x1n which I am getting, but immediately I will pad M minus 1 0 to adjust both of this to length L plus M minus 1. I obtain a circular convolution of y1n, which is again of length capital L plus M minus 1. But here, this last M minus 1 points, I have to overlap and add with the first M minus 1 points of the next section convolution, which is y2n. And how to get y2n? Y2n I am getting from this x2n, which is the next L sample, next frame, pad M minus 1 0, perform again a circular convolution of this hn with this 0 padded x2n, get y2n, and whatever be the first M minus 1 points of y2n is overlapped and added with the last M minus 1 points of y1n. Similarly, last m minus 1 points of this y2n will be added with the first m minus 1 points of this y3n. And how to obtain y3n? It is again the circular convolution of x3n, which is 0 padded with capital M minus 1 sample with hn, right? So that figure indicates a simple overlap add method. Get the sequence, right? Do the circular convolution, do the overlap and add, and get the yn streaming. So you have a xn streaming, yn is also streaming, which is filtered version of xn. So in that way you have a real-time processing. So here I have formulated one example where hn is only 2-point filter for simplicity, 3, 2, and xn is a long sequence. Compared to this hn, it has a very large length. So obtain the convolution of this x and h using overlap add method by taking capital L equal to 3. That means my frame size is 3. So I have to divide this xn in a chunk of 3 samples. So first I have to take x1n 1 2 minus 1, x2n 3 2 minus 3, and x3n minus 2 minus 1 and 0. Now this is having length 3. This section of this is having length 3. This is having length 2. So when I want to get the answer of the linear convolution, it should be 3 plus 2 minus 1. So it should be 4 points. So I have to do 0 padding here, 2.0 padding here, and rest of the 0 padding I have to also do here, right? So I have to do one sample 0 padding in each x1, x2 and x3 again. And then I will find the circular convolution y1n equal to x1n hn, y2n x2n hn, y3n x3n hn, and I get y1n, y2n, y3n, but I have to overlap capital M minus 1 points, last M minus 1 point of y1n with first M minus 1 points of y2n. So you can calculate this M minus 1 very easily. This M is 2. So 1 point, last 1 point of y1n I have to overlap and add. Similarly, last 1 point of this I have to overlap and add, and I can reconstruct, or rather I can construct a signal yn, right, in this way. You can verify this. So again a very simple operation. This diagram clearly illustrates the simple overlap add operation. You can easily do it and get this answer, right? So we end here this DFT, and in next module we concentrate on efficient computation of this DFT via FFT algorithms. These are fast Fourier transform algorithms.